the time constant tau for an RL circuit. Earlier in this course, we covered RC circuits, that is, circuits having resistors and capacitors. To review, the equation for the time constant of an RC circuit is R times C. Recently, we've been studying RL circuits, that is, circuits having a resistor and an inductor in, for us, series. The equation for the time constant of an RL circuit is tau is L over R. Bit of trivia, we're studying RL circuits, but if you had an RLC circuit, then you'd have resistors and inductors and capacitors, all three. We established previously that the exponential parts of the time-dependent behavior equations for RL circuits can be written like this. This was in 2 previous videos. Below the appropriate expression, write either decaying or climbing. We have talked many times that a climbing graph has this pattern, 1 minus e to the minus something, and that a falling graph or a decaying graph has that pattern. So let's combine our part 1b answer, which I've rewritten here, with each equation above to yield 2 new equations that don't contain either R or L. Let's just write the exponents. If we put those in there, it looks like we're going to get 1 minus e L over R, and this one has R over L, so it looks like my tau is going to end up in the denominator here. How about here? Same thing, like that. Below these part B expressions, when the time equals tau, write the value of each expression to 2 decimal places. This was a while ago, but we said that the fractions that you wanted to keep in mind, remember for half-life it was 0.5. Whenever we are using time constants in electrical circuits, the 2 fractions to keep in mind are 0.37 and 0.63 to 2 decimal places. Now, which one is which? This one is the 0.631, and this one is the 0.371. So that means in one time constant, this much has happened, that fraction. And it depends. If we're climbing, then we've gone 63% of the way up. If we're falling, we've fallen to 37% of where we were. There are obviously more decimal places here, but it's very convenient to remember to 2 decimal places, the 37% and the 63%. All right, very easy. Let's determine the time constant of this circuit here, and let's include proper units. Well, the time constant for an RL circuit is L over R. That means that we have here the inductance is 3 henries, the resistance is 15 ohms. That looks to be 0.2, doesn't it? And what's the unit for tau? Well, you could say henries per ohm, and that's fine, but it's better that you conceptually understand that a time constant is an amount of time. So seconds would be better to put there. Technically, we couldn't count it wrong if you put henries per ohm, but seconds is better.